Okay, so welcome back. So we are doing lecture 6. I mean, I don't know about the numbering, but we are talking today about the physical layer. The physical layer, which, as you know by now, is basically the first layer in the OSI model, or the first layer in the TCP/IP even. So the physical layer deals with physics, deals with signals. So what we'll be doing the next weeks, this week moving forward, every week will be about one of the layers. We'll be talking about the physical layer now. Next week, I'll be talking about the MAC layer or the data lake layer, which is on top of it. And then I'll be talking about the network layer, which is in charge of routing. And then finally about the transport layer. Because the others we discussed in other courses, okay? So every chapter focuses on one of the layers, and we will go on, hopefully all the way to the application layer. So when we discuss the physical layer, we talk about two major things. One is data, the other is signals, okay? So data and signals. So everything I'll be talking about today has to do with data and signals. And when I talk about signals, there are two kinds, analog and digital, or simple and composite as well. So we'll be talking about all this today, so focus. And the whole point is, I have a communicating device, like a computer, like a phone, again, like a tablet, doesn't matter what device, like a sensor, like a robot, and I want to communicate over medium. Hence, I have data on one side. I want to end up with data on the other side. To do this, I have to use a communication medium. Hence, there's a lot of conversions happening from data to signal, then from signal to data again. And that's what we'll be talking about today. So yes, if I want to send the data, of course, I have to convert it to an electromagnetic signal, hence to use the communication medium. Either in air, like wireless, or an actual cable. So an actual cable has something called a carrier frequency, something in it. There's a signal in it. Yeah, that's why you don't get electrocuted, because the signal is so small, unlike an electrical cable. And that's an electromagnetic signal going through this. So if I'm plugging this and I cut it, I put my hands on it, you will feel something. It's not an electric signal, it's an electromagnetic signal. Okay, and that's the whole point of data communication. Okay, so yes, as we said, both things, data and signal, could be either analog or digital. So one more time, data is what I have. What I want to send is signal. To be specific, electromagnetic signal. The data itself can either be analog or digital. Typically, analog is what? What was the original analog signal? Analog data, sorry. Huh? Not telephone. Telephone line is the actual signal, right? So what was the data? The original data is analog. Voice, of course. That's analog. It's not rocket science, it's analog. Voice is analog. Okay, sound is analog. So that's analog. Typically sine waves. It's not discrete. Okay, continuous versus discrete. So analog data do exist. Obviously, digital data, it's obvious. What's digital data? Example. What's an example of digital data?
Binary.
Image. Okay, but obviously, computer stuff, email, text, everything's digital. All these are digital. What you're looking at now, my PowerPoint slides is digital. That's why we say now, our generation, your generation, to be specific, is going through a digital transformation. We're changing everything to digital. Again, digital government, e-government, or e-health, even your healthcare, your insurance, everything is digital. So we're digitizing everything. So yes, so data can be either analog or digital. The signal can be either analog or digital. So we have either analog or digital data, analog or digital signal. So yes, data can be either. So when I talk about analog, typically I'm talking about continuous. Okay, I don't know if I stop recording now. So if you're online, I think I'm gonna quit this online. Or I could mute them. 1 second. Stop recording. This is so annoying. Pause. Oh, pause. Sorry. You're right. Okay, we're back. So yes, data can be either analog or digital. Signal can be either analog or digital. When I talk about analog, I'm talking about continuous values. One more time, continuous. Continuous, if you learned any mathematics in high school or before that, continuous is like this. Imagine my hand. So your heart beats. It's continuous, you know? The signal of it. You see, if anybody's seen their heartbeats, anybody? Yeah, you've seen it on the monitor. Yeah, that's like this. That's a continuous signal. Inshallah, it's not discrete. If it's like this, then you're dead. Okay, so that's discrete. Discrete's like this. Okay, so yes, ideally, the plan would be look at what kind of data we have, what kind of medium we have, because the medium could be either digital or analog. Who could give me an example of an analog medium? Telephone line. Give me an example of a digital medium. Fiber optics, you know, simple. Yes, it's using light, but it's still digital. Still light or no light. Light or no light, typically. Or coaxial, to be specific, right? The coax can be either broadband or baseband. What is baseband? Digital or analog? It should have been a lecture before this. Baseband, digital or analog? Habibi, good luck in the exams. Good luck. What the heck are you doing quizzes? Okay, you have everything in front of you. Just Google, search. Okay, good luck in the final. There's no Google. There's no search. Okay, there's no Control F. That's the fastest thing people learn. Control F. Let's see if it's somewhere. Okay, yes, of course, baseband is digital. Broadband is analog. Okay, so that's another example. Okay, move on. So as I said, signal can be either analog or digital. When I talk about analog, I talk about continuity. So infinite number of values. Okay, so it's continuous, as I said, versus discrete. And digital signals typically have limited number of values. Typically, again, digital would be 0, 1. It's not always 0, 1. It could be 0, 1, 2, 3, 4. You can have different levels. Okay, so that's the idea of digital. So if you compare an analog and a digital, I think this is very obvious now. Based on what I just said, you could see analog is this continuous flow, okay, and digital is more specific values. You know, we call this a step function sometimes, right, or stair function. So it's either 1 or 0 or 2 or 0. It has specific values. You know, it's continuous. It could be anything, right? 0.0001, 0.000, because it's continuous. All the values in my x-axis have a y-axis, a value, right? All of them, because it's going to keep on going. There, no. Some of them don't, right? Like all these values have the same y, right? And all these values have the same y, which is 0. And all these values have the same y, which is minus 1. I say y. Again, whatever that value is, typically voltage. Typically voltage, right? How many voltages? Okay, or what? We're talking about power. Okay, so we commonly use periodic analog signals and non-periodic digital signals. Yes, we usually, when we talk about data communication, we end up using periodic. I'll tell you what periodic means. Periodic means it has a period, meaning it repeats itself. Period meaning it repeats itself. A signal that repeats itself. And the famous periodic signal is famous. Sine wave. Thank you so much. Bonus point for you. What's your name? Who said sine wave? Somebody with the mask. Okay. What's your name?
Rayon.
Okay, thank you. We'll talk later. Okay, I don't know. Akshita, if you can hear me, there's a guy called Rayon. Yes? That was it?
Rayon. And
Crayon? Put the mask. Tell me your name.
R-E-Y-O-N.
R-E-Y-O-N. Rayon. Okay, like Ryan? Rayon. It's a different version of Ryan. Okay, Rayon. Akshita. Okay, very good. Thank you. Very smart. So as we said, sine wave, cosine wave, tangent, cotangent, the famous trigonometric functions that we've taught you in high school, all of these are periodic. They repeat themselves. They're always like this, right? Like this, repeating themselves. That's what we call periodic. So periodic analog signal is very common, and non-periodic digital signals, non-periodic meaning it doesn't repeat. So like that. This is non-periodic, right? Is this periodic or non-periodic? Of course, non-periodic. Except if I show you here the same picture again, if I cut it and paste it, cut it and paste it, it becomes periodic. But typically it's not, right? It went down, went up again, went down. It's not consistent. This is also, is it periodic or non-periodic? Yeah, it was here, as you said, periodic, then load went up, it kind of changed, but the period is the same. It's still periodic. Yes, the amplitude changed. This is called amplitude. You need to know this. Okay, this is what this whole lecture is all about. Amplitude is the height of the peak. Yes, the amplitude changed, but it's still the same, more or less the same period. Maybe the frequency changed, right? Frequency meaning how fast you're going. So these are terminology we're going to be teaching you today, or I'll be teaching you. Period, frequency, wavelength, amplitude, and phase. That's what you need to know because we're talking about the physical layer. When we go up, we don't care about these things anymore. When I go to the data link class, the physical layer is in charge of this. The physical layer is in charge that the signal comes in, converted to data, and I'm done. I being the physical layer. It's done its role and gives that data to whom? The physical layer gives it to whom? Data link layer. And the data link has another job. Put them in frames, figure out if there's errors, correct them, detect them, do a MAC layer, medium access control, like Wi-Fi, that's MAC. Wi-Fi. The guys talked about 802.11 today. That's a MAC layer protocol. They're talking about layer number 2. You see? So what you need to understand when you talk about networking, each layer has a job. And once they're done, you just give it more or less in an envelope to the layer on top of it or below it, depending on what side you are in the communication system. Are you sending? You're going down, receiving, it's going up. Okay? Yeah? We good? Excellent. Okay, so let's continue. So as I said, typical are periodic analog and non-periodic. We'll be talking about all of them, but typically the most common are periodic analog signals and non-periodic digital signals. So when you talk about periodic analog signals, typically we have two kinds, as I said at the beginning, simple or composite. As the name sounds, simple meaning it's a simple sine wave, more or less. The sine wave is kind of the mother of all analog signals, the sine wave. So anything, a piece of it would be a sine wave. Now, if it's a composite signal, what do you think it means? If it's a composite signal, without reading here, what do you think it means? I said simple sign, a simple signal versus composite. Did I mention it here? I did. Okay. So yes, of course, a composite is a combo. Composite, I need to compose it. Actually, I need to decompose it. It's composed from multiple sine waves. So if I send a signal, for example, I talk with me at the same time. Hello, what's your name? Somebody say something. Hello, what's your name? Yeah. Your signal overlapped with mine, so it became a composite signal when they received it there. Okay? To analog, by the way. Analog data in this case. And when it came to the air, it became signal. When it left my mouth, it was data. In the air, it's signal. But that's what's carrying it to your eardrums. Okay? Does that make sense? So yes, very simple. As the name sounds, simple signals are simple sine waves. Composite are multiple sine waves. Okay, and I'm showing you a picture in a second. So our goal, obviously, as you would expect, if I have a cable running from California all the way to Dubai, right? The big cable over the oceans, right? Under, and so you saw a video I showed you, and I'm sure you've seen many of them. These big chunk cables, and then you have a server, a chunk, and so on. Imagine, what do you think that cable is carrying a simple wave, a simple signal? Why not? Why not like one person sending a signal? Why not? Too slow or what? It's not about slow, which is going to be super fast if you send one signal. It's about, it's nonsense because, I mean, we're sending billions of dollars of cables from one continent to another. Obviously, I would have a multiplexer. Obviously, I'm going to send way many signals on it. You know, you send yours, I send mine. I mean, all these people connecting to this thing are sending over this thing. When it comes here, what do we receive? A composite signal, right? We need to decompose it back to the original signals. And that's the famous, super famous, do you know who came up with this? One of the geniuses of mathematics? Nobody? Anybody? French names?
Oh, sorry, wrong class.
What are you guys smoking these days? I need some of it. Wallah. We're so happy. I'm sure he's high. Okay, good. No, but serious now. Let's go back. Need to go back to you. Need to go back to you. No, seriously now. What was that? Yeah, the guy who came up with it, French. He's French. Anybody knows a French mathematician? You don't know a single French mathematician? Joseph? Ah, yeah. Fourier. Yeah, you know Fourier? Yeah. Of course, you know, the guy has been that for 100 years. Yes. Bonus point for you. What's your name? Yulia, yes. Akshita, Yulia. Okay.
Yulia.
Akshita is still with us. Okay. Anyways, just back up. Somebody could help me here. Can you help me? Yeah. So just in case she's not keeping for today, we have Yulia and we have Ryan. Raymond. Sorry. Anyway, so let's move on. Yes, Yulia, 100% Fourier. Fourier, the famous mathematician, is called Fourier. He came up with something called Fourier analysis, which is again part of the lecture. He's the genius who figured out, you know what? Any signal, there wasn't signal back then. He was dealing with mathematics. That's what you need to know. Mathematics fed into communication, fed into networking, fed into engineering. Without him, we would never have computer networking today. Not many people know this. So that's what we call Fourier analysis. He said, one second. He said that any composite signal can be decomposed back to its original form. And not only this, he gave us the formula for it. Once we have that, khalas, it's easy now. I could send 100 and then I could go back, if it's periodic, I could go back and decompose it. And that allowed us now to share a medium. Any medium, we can share it now. Before that, it's impossible, before Fourier. Obviously, Fourier came before networking. So we are basing it on. So sorry, my friend, yes. No, of course, it could be digital. No, yeah, digital, but yeah. If the medium is a digital medium, yeah, so if it's a digital cable, then of course it's going to be digital. Okay, so very good. So let's move on. So one more time, for those who don't know by now, this is what we call a sine wave. Okay, sine x, y equals sine x. That's how it looks like. You could plot it on your calculator. That's what a sine wave is, guys. So let's talk about power a little bit before we move on. For example, there's something called RMS. Root mean square. Okay, so when we talk about a sine wave, typically the amplitude, one more time, let's talk about this. The amplitude is the power. Okay, so if I'm looking at electric sockets, before we go to networking, the electric socket, you know, in Dubai, I think it's 220. 220, right? 220 volt, 220. In the States, it's 110. You know what I'm talking about, right? You know when you get like electric. So what you're actually looking at, many don't know this. Of course, what you're looking at is the peak amplitude. That's the peak. The maximum is 220. The maximum is 110. But it's an alternating current. Typically like this, you know, what is coming through it, right? So it's not a DC, it's an AC, most likely, right? So the idea is, for example, if I told you in the US, I think it's 110 to 120. Okay? What you don't know is this is what we refer to as the root mean square. So basically, you have to multiply by square root of 2. That's what root mean square. Root mean square. To figure out the peak amplitude. So if I told you the power is 110, what's the peak amplitude? It's a radical 2 times 110, which is typically 155. That's the peak of the wave. That's what they refer to, just in case you see this something. Okay? So yes, both of these have the same phase and frequency, but they have different amplitudes. As I said, today we talked about 3 things: phase, frequency, and amplitude. Very important, you know. By the way, I downgraded my lecture. Before this lecture, it used to be 150 slides and web detail. Like we'd solve sines and cosines. Over time, as I said, my expectations went down. So now I just focus on what's really important for you. I'm serious, okay? So that's why whatever I give you in the lecture today is what is you're required to get. If you find something extra online in my Moodle, it's not required. Only what I teach, okay? That should be clear. Okay, back to this. So one more time, amplitude, frequency, and phase. So these have the same frequency. They have the same phase. I know you don't know what phase is by yet. I'll explain. But for now, let's focus on amplitude. Amplitude is peak. The peak volt or the peak watts. Okay, depending on what my unit is. So this is my amplitude. The peak of it. The peak. is what we refer to as an amplitude, especially if it's periodic, it's very easy. Okay? So again, for you to understand, so if I'm talking about sound waves, speaker, if I raise the volume, what am I raising? The amplitude. If I raise the volume, I'm raising the, if anybody does DJing and music mixes and so on, you are dealing with amplitude, frequency, and phase. If you're overlapping two music sounds over each other, you have, again, a composite signal. And you could play, like, you could filter out something, you could filter out noise, you could play around with it. You are dealing with signal at the end of the day. Yes, it's not a communication signal, but still a signal. Okay? Are we good? Yeah? So one is amplitude, yes. The voltage of a battery is a constant. Again, that's obvious. In case you don't know, a AA battery, AAA, that's constant. But still could be considered as a continuous signal. Okay? So the peak of an AA battery is 1.5. So if you look at an AA battery, the peak that they will have is 1.5. So typically, it's a constant of 1.5. That's another thing. Different than, of course, as I said, a socket. Okay? So number one that you need to remember is frequency and period. Frequency and period are inversely proportional. Very simple. To be more specific, they're reciprocals. Reciprocals meaning one is equal to the other, one over the other. Okay? If I have one, I can find the other. So why? By definition, frequency is this. Pay attention. So this is basically frequency. How many oscillations per second? Typically per unit time. So again, imagine my hand is oscillation. See? So suppose I did 5 hits in 1 second. What would my frequency be? 5 what? Unit? 5 hertz. To be more specific, 5 hits per second or 5 cycles per second. Typically, how many cycles I'm getting per second. Now, let's do it again. So I did, let's say 10. So that my frequency would become. So now you kind of understand what's frequency. Frequency is basically how fast I'm moving as a signal, you know? Am I doing quick cycles? You know? How many cycles per second? So let's go back to cycles. So this is the cycle. Again, if you don't know what cycle is, the time you come back to where you started. So I'm here, right? So typically I'm here. Again, say, why not here? No, this is going down. I need to be going up. Okay, so I go up. I'm going up again. This is where I started. That's called a cycle. That's one whole cycle. Then another cycle, another cycle. So in this case, suppose this was 1 second. Suppose this time was 1 second where my finger is. What would the frequency be? 3 cycles per second, or hertz. Hertz is equal to cycles per second. Does that make sense? So get used to it. Be comfortable with it. Because obviously, if I wish I had a simulator. I had that. I don't have time now. But if I hold this here, and I squeeze it, so I make these peaks closer to each other. You know, do you think the frequency will go up or down? Of course up, because I'm doing more cycles in 1 unit, right? I'm doing more. Does that make sense? So one more time. Amplitude is the height. This where my finger is from here to here. That's called amplitude. Typically the peak amplitude. That's what we care about most. And frequency is how many cycles per second. And period is the inverse, is the reciprocal of my frequency, which is 1 over. So if my example had 3 cycles per second, so 3 hertz, what would the period be? 1 over 3. What's the unit of period? Second. Very good, very good. Thank you. 1% second. So period is time. Frequency is cycles per time. Okay? So for you to understand a little bit more, by definition, period is how much time I need to complete. Yeah. So he says 1 cycle. Yes, very smart. 1 cycle. Okay? The time I need to complete 1 cycle is the period. And how many cycles per second is the frequency? You see the relationship? They're inverse. 1 over the other. Again, very simple. If my frequency is 3 cycles in 1 second, how much time each cycle took? 1 over 3. You see? That's how we got the formula. Now we know. That's what period means. Are we good? Yeah, let's move. Okay, so this is another example. I could go quickly. So you can see here, 12 periods, basically 12 cycles. You can count them. And how much? 1 second. So 12 in 1 second. Obviously, the frequency would be 12 hertz. And here we have 6 in 1 second. The frequency would be 6. Okay, very simple. Or 6 cycles per second. Are we good? Yeah. So again, obviously, I could be clever and say, you know what? It's not 1 second. This is, let's say, 0.5 from here to here. So what would the frequency be? Yeah. What would it be?
24.
24, of course. I mean, again, it's not rocket science. So if this is 0.5 second, I have 12 cycles in half a second. How many do I have in 1 second? 24, right? Double, half of it, right? I mean, it should be fast. It should be fast. It should be batata, right? It's quickies. You should just look at them. I get it. You don't have to overthink things, okay? Yeah, so what's your name? Who said 24? You said so confusing. Yeah, what's your name?
Abdullah.
Abdullah? Don't look like an Abdullah. Okay, Abdullah. Yes, Abdullah. Achita Abdullah. Thank you, Abdullah. Very smart. Thank you. Okay, so let's move on. Oh, okay, so now we have caption. Nice. High tech, huh? Now we have caption. Computer, we have caption. Oh, good. Okay, let's move on. So let's move on. So again, units of period and frequency, as I said, period is time, frequency is hertz. Again, obviously kilohertz, megahertz. By now you should be comfortable with this, huh? If you're not, as I said in the final exam, again, now the focus is final exam because we started the second half of the semester. In the final, you could get the cheat sheet, of course, in like a corner somewhere. Make sure to put these because we'll have calculations. You know, we've done a lot, network management, little bit even physical there as well. So yes, hertz, kilo, mega, giga, tera. Make sure you know that going up, we're multiplying by 1,000. I mean, just make sure you're comfortable. It's the same thing with seconds. You know, going down, second, milli, micro, nano people. Okay, one more time, milli, micro, nano people. So we're going down, we're dividing by 1,000. Okay, we're dividing by 1,000. Okay, so the power we use at home has a frequency of 60. What's the period can be determined? So what is this? 1 over 60. It's not rocket science. Just to make sure we're comfortable. Again, make sure you're comfortable with the units. So it's 1 over 60, which is 0.0166. Okay. Let's be comfortable. This is in second. By default, it's second. If this was hertz. If not, I have to be consistent. This was kilo. I need to convert it, right? Just make sure you're comfortable. With the exam, I told you this is the correct answer. But sometimes I say, in my percent, in millisecond. Just to make sure these are trivial things that we should know. Of course, again, this is basically 60.6 million. One more time. If I'm going from second to milli, what do I do? From second to milli, what do I do? From second to milli, second is bigger. If I'm going from second to milli, what do I do? Multiply by 1,000. Take it. So divide by 1,000, multiply by 1,000, so it becomes 16.6. Okay? Are we good? Yeah? Okay, perfect. Let's move on. Again, another simple example. Period is 100 millisecond. Again, be consistent. If I want to find it hertz, I have to change milli to second. And then to, again, easy. So we do that quickly, and we get, in this case, the frequency is 0.01 kilohertz. If I want, or in hertz, you can keep it. It's fine. 10 hertz is fine. Okay? Because it says I want it in kilo. It should be easy stuff. So let's move on. So frequency, as we said, is the rate of change with respect to time. In the case of signals, it's basically how many cycles per second. And again, of course, high frequency, meaning I change a lot in a short period of time. Of course, if I change slowly, it becomes low frequency. If you don't change at all, then it has a zero frequency. If you change instantaneously, has an infinite frequency. So frequency would be infinity. Okay, because imagine like super fast, then the period will be so small, right? Which means again, typically micro or even less than micros. Therefore, you could imagine I'm dividing by 0 almost, right? This because it's 1 over period. So if you divide by 0, it's infinity. Of course, it's not really 0, but it's very close to it. Okay, that's why it's going to be a huge number. That's why we say we call it an infinite frequency. So now, the trickiest among all these is the phase. Okay, this is where a lot of you phase, we pronounce it with Z, phase, not face. Okay, yes,
Just a question. For a phase, right?
phase, yeah.
Thinking like it's the start and the end point.
No, it's not. Phase is the angle it makes with the x-axis. I'll talk about it. So
you said in the previous, they
Yeah.
have the same phase,
they have the same phase, meaning they're moving together. The angle they make
but if it changes, like for example,
shift.
yeah, if it shifts, then it changes phase.
Yes, but it still could start together, but you could have different phase if one is moving at a different direction. So, for example, if you're going up, I'm going down. We started together, but it's different phase. It's actually completely opposite phase. You're plus, I'm minus. I'll talk about it now. But yes, thank you, Abdullah. Well done. So yes, phase, and sometimes we call it phase shift. Okay, so it's because it has to do with shifting. So phase, we're talking about an angle. Talking about the angle that you're making. So you're talking about what's the unit of angle? Unit of angle, degree or radian. So this is what phase is. The unit of it is degree or radian. Radian, I'm talking about pi, pi over 2, 2 pi's, and so on. And degrees, of course, here are 60 degrees or below. Because one more time, a full cycle is how much? What do you think? A full cycle is how many degrees? A full cycle, 360. Thank you. Because it's a circle. A full cycle, you think about as a unit circle. You go back to your basic mathematics, okay? Or 2 pi. The first one is a pi, the other one is a pi in radian. So be comfortable with this. You have to be, one more time, this is the only course in computer science or IT that has to do a little bit mathematics. Everything else is algebra, basic stuff, discrete math, not too much in it. But this is the only one that has a little bit in it. So that's why we want to make sure you understand these concepts, especially when it comes to communication. So, where was I? Yeah, so the position relative to time 0 is what we call phase. So let's look at it. So sometimes we call it phase shift. So you can see here, this sine wave, the original sine wave, that phase is equal to 0. Because you start at 0, going up. Totally. Now, this one, if I hold it and I shift it, imagine I take this whole wave and I carry it backwards. To be specific, I carried it backwards. I shifted it backwards. By how much of a cycle? This thing, how much of a cycle is it? 1/4 of a cycle. You all agree? Because look at it. It's like 1 piece, 2 piece, 3 piece, 4 piece. Any cycle, I could cut it into 4 pieces like this. Right? So, 1/4 of a cycle. Remember, a cycle is 2 pi or 360. So it's going to be 2 pi over 4, right? So I shifted it by 2 pi, because the whole thing is 2 pi, 1/4 of 2 pi, which is basically 2 pi over 4 is what? Cancel 2. It's pi over 2 pi over 4 is equal to pi over 5 over 2. So that's why, as you see, this is pi over 2 phase, which is basically 90 degrees. The same thing. The whole cycle is 360, and I took 1/4 of it backwards. Because, again, it's easier for you to understand. If I want to get this picture, from this guy, what should I do? I need to hold it and push it forward by how much cycle? Look, by quarter of a cycle. I need to move it forward by quarter of a cycle to get the original sine wave, right? Therefore, my phase shift is plus pi over 2 or 90, which is 360 over 4. That's how we got it. Does that make sense? Because I could cut it smaller if you want. But typically, we're going to cut it on a symmetrical basis, like this. Most likely. That sounds good? Let's do one more. Again, as you can see, how much of a cycle is this? Yeah, so half a cycle. Half a cycle, which is basically 2 pi over 2, which is pi, which is 180. Again, pi is 180. I say pi because I'm going to use pi as a comfortable radian. Pi is in radian. This is in degrees. So 90 degrees, 180 degrees, it's something shown here. Oh, this is consistent. The text is fine. I'm not checking it out. It's fine. Not bad. I mean, this is good for those who have like issues in hearing. Okay. In here. So let's move on. So are we good? So phase shift, frequency and amplitude. 580. 580 or 180 degrees. 100%. Okay. Okay, so a sine wave is offset 1/6 of a cycle. Again, I like the picture there, but now it's 1/6, not 1/4. With respect to time zero, what is the phase in degrees and radians? Again, I think we know it better, right? 1/6 of the cycle, so 360 degrees divided by 6, or 2 pi divided by 6. So you can see again, 360 divided by 6, which is 60 degrees, or in pi terminology, is pi over 2. So 60 is pi over 2. We don't know that because pi is 180. 180 over 3 is the same. Okay, so 1 in radian. Again, what is pi? Pi. 3.1415. It's basically irrational, never finishes, so you can find that later. If you divide it, you get this. Okay? Are we good with phase, amplitude, and frequency? Okay. Let's move on. So wavelength, you can see wavelength is basically the distance of a cycle. You know, so I started here, I ended here, the distance. So what's the unit of wavelength? The distance. What's the unit of it?
Meter.
Meter or micrometer usually, right? Or millimeter, but it's distance. You see? Period is time. Wavelength is distance. Frequency is hertz or cycles per second. So you should be comfortable with these units. Phase is angle, degrees, or radian. Okay, so what's your name? You're the same. Okay. Ryan, Achita. Ryan, same Ryan. Okay. Okay. Sorry, you have another question?
Not in this case, but suppose you don't give us a full wave, like very small. So can I take?
No. I will give you a full wave always, of course. It's continuous. It never ends. I mean, this is like 3 dots. Yeah.
Very small.
Yeah.
I just take from one amplitude to the other.
Yeah.
It's the same.
From the big part,
To
from
get
the
the wave.
peak.
Yeah.
Yeah, of course, from here or here, same thing.
Yeah.
Actually, by definition, wavelength
From
is the
from-
distance between 2 consecutive
Yeah.
maximas or 2 consecutive minimas. It's totally fine. Or where the cycle started. Yes, 100%. Okay, so now we start making it more interesting. So when you talk about signal processing and communication, they have something called time domain and frequency domain. And this is where Fourier came. I'll talk about Fourier in a second. But yes, we have time domain and we have frequency domain. So you could see what we've been talking about basically is the time domain. I say time domain meaning my x-axis is time. So over time, how is my signal changing? Okay, very simple. That's what we call time domain. This is like a signal. The frequency of it is 6 hertz. Why is it 6 hertz? Because 6 cycles a second. So presumably this is a second. So we have a cycle, another cycle, another cycle. That's how we got the frequency. The frequency is 6 hertz in the time domain, and the amplitude. What's the amplitude? 5. So we know the amplitude, we know the frequency, and in this case, the phase. What's the phase? This phase 0, because it started here and went up and to. So far, so good. That's what we call the time domain. That's very difficult to deal with. We don't like to deal with the time domain, especially if I have a composite signal. I have things on top of each other. This is very confusing. Usually, when we deal with signals, we deal with them in the frequency domain. And the frequency domain is so easy. If I want to convert this to this, my x-axis is frequency. So I have how many signals here? How many signals in this example? 1 signal, and the amplitude of it, 5 volts, and the frequency of it is 6 hertz. So I come here to 6 hertz. I make it a spike. Okay, because it's a periodic signal. Because this was a periodic signal, in my frequency domain, it's going to be denoted by a spike. was pi. The height of it. See how easy? How this is in the time domain and this is in the frequency domain. And now you can kind of visualize what the next step is. So this was a composite signal. How would it look here? Yeah, 100%. Very smart. What's your name? Danny, huh? Cheetah, Danny. Bonus point. And you keeping track of it as well. That's the issue. Well done, Danny. Very smart. As Danny said, of course, this was a complicated composite signal. If I change it to a frequency domain, it's going to be so easy. It's going to be like spikes here. You know, 1 year, 1 year, depending on what the frequency is. That's why the frequency domain is easier to deal with, especially when I'm doing processing, data communication. So yes, a sine wave in the time domain is represented by one single spike in the frequency domain. As I just mentioned, the frequency domain is more compact and allows us to kind of deal with composite signals. Again, very similar to what I was talking about. As you can see here, it's very complicated, right? Like humans, we can't deal with this, especially if I have 20 of them on top of each other, right? So obviously, because they're all periodic, it's easy, like with magic, I get this. So what is this telling me? What is this telling me? How many signals do I have? 3. Again, 3 different amplitudes, 50, 10, 5, and 3 different frequencies, 0, 8, 6, based on what we have. You could do the calculation, and you see you get the same answer. Yes, sir. Huh? It doesn't matter the phase here. Frequency domain, we cannot know the phase. We can't show the phase shift in the frequency domain. They could have different phases, but it doesn't show at the frequency domain. A very good question. Yeah. Frequency domain only focus on amplitude and frequency, assuming they have the same phase. Amplitude is the peak. Yes. What? Yes, from the domain. Yes. Then 5, and the last one, the blue one is 50. That's a signal. This is a signal. It's a constant signal. The blue one. It's not a sine wave. But still, as a 15, as you can see, the frequency of it is 0 because it's constant. There's no frequency. It's not moving up and down, right? Yes. Good. Okay. So again, obviously, usually we have composite signals in data communication, and this is where Fourier came in. The famous Fourier analysis. He said any composite signal, he said that this is a famous theory, it's called Fourier's analysis. And he came up with a technique. We used to teach it, by the way, but now I'm skipping it in this course. But anyway, he said any composite signal is a combination of simple sine waves with different frequency, amplitude, and phase. He said any composite signal you give me, it doesn't matter, any composite signal, I could guarantee that I could decompose it using a formula. Okay, and that's the magic, and that's what allowed us to do a lot of things. To be more specific, if my composite signal is periodic, then the decomposition will give me discrete frequency. So one more time, if I have a composite signal that is periodic, it has a period, it's repeating itself, then when I decompose it, I will get discrete frequencies. Now, if my composite signal is not periodic, yani all over the place, not periodic, composite signal, then the decomposition will give me sine waves with continuous frequency. It will not be discrete. It will not be discrete like this. It will be continuous. Very, very interesting. Okay, let me just move a little bit past Abdullah, sorry, and come back to you. So let's look at an example of a periodic composite signal. So a periodic composite signal, again, could be an alarm system, whatever it is. This is an example of, it's an example of periodic. You agree this is periodic? Very obvious, periodic. And of course, it's not a sine wave, it's a composite, right? This all here is a sine wave. Of course, if I give it to you, even to me, if I look at this, I have to be a genius to know what the original was, right? Anybody knows what the original was? Of course, you can't. It's not simple. It's not something that, I look at it, decompose it. But if you go back, I could tell you exactly what this is using Fourier analysis, okay? Using Fourier analysis, that's what we get. You see? These 3 signals superimposed on top of each other is this guy. What you're looking at here is these 3 guys. We cannot know. Impossible without Fourier analysis to know what the original was. After I look. So Fourier analysis allowed us to do this. So you can see this is my time domain. I have 3 signals, again with colors to make your life easy. Of course, in the frequency domain, I'm going to have 3 discrete spikes. Okay? 3 of them because I have 3 signals. Does that make sense? Yeah? Again, because this was periodic composite signal. Now, again, we get spikes. Discrete. Spike meaning discrete. Okay? Now, if it's continuous, what do you think it will look like here? So one more time, this was periodic. I get discrete. One more time, periodic. I get spikes. If this was a non-periodic composite signal, what would I get here? Continuous. That's what Fourier told us. Continuous, meaning there is a value for every value here. So how do you think it will look like? Do you think it's going to be spikes?
Going to go up.
Kind of. So yeah, a line. You know, like this. There'll be lines moving horizontally. There'll be spikes because this is discrete. Something like what you said. Yes, let's see it. So suppose we have a non-periodic signal, which is very common. Again, microphone, voice. Like, imagine I was like, you know what? When people do presentations in my courses, if they're monotone, you know what monotone is? Like a robot. That's called monotone, and that's the worst thing in presentation. You know, there's no action. Huh? Usually, I would say this monotone could be periodic, right? Could be like same tone, continually, you know. Of course, a normal person like us would be non-periodic. And like my books, now, if you're recording it on a phone and you see the wave, you see it's not periodic, 100%. So something like this, right? So this is not periodic. Opposite, it is opposite. It could be 5 people talking at the same time, some background music, stuff happening. So it's not periodic. Again, for ESL, we can decompose it. However, look at the decomposition. This is my frequency domain. We don't have we don't have spikes anymore. What do we have? We have a continuous function. What does continuous mean? Meaning they have a value for each one of them. See, frequency, let's say is 1. I have an amplitude. Frequency is 2. I have an amplitude. Frequency is 3. I don't have spikes anymore. It's not discrete anymore. Okay, you see, how can I draw this by looking at this? You can't. I mean, we have to do analysis, Fourier analysis. But I will give you an example on this.
But sir, it still doesn't decompose how many signals.
It does. Infinite. I mean, I'm saying it's continuous. It's continuous. Every one of my hands is a signal, my friend. Before it was discrete, 3 signals. Now it's continuous, meaning you have tons and tons of them between 0 and 4 kilohertz in this case. Okay?
Like we can't see it.
No, you can't because it's continuous. Our goal is not to see it. Our goal is to decompose it only. Good. So now, by definition, the bandwidth of a signal is the difference between the highest and lowest frequency. So the maximum minus the minimum, is my bandwidth, of course. I mean, by now we should know that's to the range of frequencies. So you can see here, in this case, again, is this discrete or continuous? Do you think the original signal was periodic or non-periodic? Periodic. Should be comfortable with this now, okay? Periodic. And again, is this discrete or continuous? Continuous. You think the original signal was not periodic or periodic? Not periodic. See, be comfortable with this. Now, we need to know the bandwidth. Again, the bandwidth is the maximum minus the minimum frequency. In this case, maximum was 5,000 minus 1,000. So my bandwidth is 4,000. So bandwidth is hertz, 4,000 hertz. And here, same thing. 5,000. Okay? Are we good? Yes? Good. Let's move on. So suppose a periodic signal is decomposed into 5 sine waves, which frequency is given. What is the bandwidth? Draw the spectrum, assuming all components have a maximum amplitude of 10 volts. Very easy. One more time. I have a periodic signal. Decomposed to 5 sine waves. And I gave you the frequencies, huh? So one more time, it's periodic. How would it look like? When I draw it, it's periodic. How would it look like? spikes. And again, I gave you the numbers 100, 300, 500, 700, 900. I give you. They're going to be spikes, 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 right? Assuming all of them have 10 volts. Okay? All of them would be height 10. Now, the question is, what's the bandwidth? Of course, 900 minus 500 to be 8. Right? Easy stuff. Just I'm moving slowly, baby steps with you guys just to make sure we get this because it's a bit technical. So yes, so let me just move on. So as we expected, right? So bandwidth 800 and we have okay. We good? Let's move on. So one more time now we have a periodic has a bandwidth of 20. The highest is 60. What's the lowest? Of course, if I gave you the bandwidth, I told you the bandwidth is 20. The highest is 60. What's the lowest? 40. 60 minus 40 is 20. So you should be comfortable with this. Don't panic. Oh, it's easy. You give me this, I get that. So what's the lowest? And about the spectrum, same thing. It's not rocket science yet. And the highest is 60, and I know the bandwidth is 20. So the lowest would be 40. The same thing, it's periodic. Periodic meaning I have spikes. We good? Yeah? Okay. One more example. A non-periodic. We didn't do any non-periodics. Yes, a non-periodic signal, composite. It's non-periodic, composite, has a bandwidth of 200. I know. We have a bandwidth of 200. So the biggest minus the smallest is 200. That's what you need to imagine, 200. Non-periodic is going to be continuous. Something like what I do. Maybe a square, maybe a trapezoid. Could be anything. Let's see what it is. Could be a triangle even. So has a bandwidth of 200. Hello? With the middle frequency of 140. They have the middle now. So the bandwidth is 200. The middle is 140. The middle is 140. Okay? And the peak is 20. The peak, the highest is 20. The two extreme frequencies have an amplitude of 0. Okay, nice. Let's go through this. I could use the annotation here. So one more time. Bandwidth is 200. Middle is 140 and the peak is 20. The two extreme have 0. So if I want to just imagine it really quick before I go. So I have amplitude 0 here and amplitude 0. These are okay. So the extreme, say that the two extreme frequencies, so the one to the left and the one to the right have an amplitude of 0. Of course, there is a peak of 20. Draw the frequency domain with the middle frequency of 140. The middle frequency is 140. Okay, so you can see the middle frequency is 140, and then you have two extreme are 0, and the bandwidth is 200. Okay, now if the bandwidth is 200, then the highest frequency minus the lowest frequency is 200, and we know the middle is 140. Yeah, let's think about it one more time. So this, the whole thing. So this minus this is 200, and the middle is 140. So what do you think? So what's the here? What's this? Huh? 40 and 240. If you see, it's 200, and between them will be 140. You get it? Because half of it is 100, right? If 200 meaning on each side, here is 100 and here is 100. If I start with 40, I add 100, that would be 140. As the question said, 140 is the middle. And you're very smart, my friend, very smart. What's your name? Joseph. Kachita Joseph here. Thank you. Very smart, my friend. Again, of course you can do it. It's like midpoint, So I know the middle is 140. So this minus this. So the biggest, let's call it big, minus 140 should be equal to 100. You agree? So this minus this should be 100. So B minus 140 equal 100. So what is B? Okay, so this suppose call this the maximum. Let's call this max. Let's call this min. Okay? So max minus the midpoint. What's the midpoint? 140 should be equal 100. Why 100? Because it's half of the bandwidth. So half is 100, other half is 100. Very simple. Max minus 140 equal to 100. Therefore, max equal 240, right? Max equal 240. Once I get max, خلاص. Then the min is 40 because the difference is 200. So 240 minus 200. Yes? So you should be comfortable with this. Of course, Joseph found it quickly, but some of you should kind of figure this out, okay? So anyway, so let's go draw this. So you can see, as we expected, 40, 240, 140 in the middle, and the peak amplitude was given. What was the peak amplitude? 20. This is 20. 20. Yeah. Okay. That's it. You see, this was a nice question. Simple. I should be complete. Are we good? Good with time. We're good with time. Let's move on. So non-periodic signal, again, example of a non-periodic are AM and FM. AM, FM, you're rating. These are non-periodic composite signals, okay? So one is the range of AM. The range of AM is between 530 and 1700 kilohertz. And FM is 88 to 108 megahertz. These are two examples of non-periodic composite signals, AM and FM. So when you talk about digital signals, we talk about encoding these digital signals. So one more time. If I have a signal, I need to convert it to zeros and ones. Or if I have zeros and ones, I need to convert them into signals to send, right? So my data coming from the computer is zeros and ones, right? Characters and so on. I need to convert them. So there should be a conversion. Usually, we call these encoding techniques. I used to spend a lot of time on them in this course. As I said, I kind of focus on what's important to you. In simple terms, this is a very simple example of, as you can see, a digital signal, okay? And this is my data. In this case, it's only two levels, very simple. Pay attention. So 1 is high, 0 is low. So we're only using two levels. So we can encode basically only 2 bits, as you can see. So 2 levels, I could encode 2 bits. So in this case, 1 bit, 1 level. So if I have 8 bits sent in 1 second, my data rate is basically 8 bits per second. Very simple. 1 bit, 1 level. This is definitely not used. Super slow. Doesn't do much. I mean, it's one. Imagine every bit I need a signal of a level signal. Of course, this is better, and what we use is way better, way more complicated. But for you to understand, instead of me using only 2 levels, said, oh, we could encode more. Instead of me sending 1 bit at a time, how much am I sending here? How many bits I'm sending? 2 bits at a time. Of course, that would make this faster or this faster. Of course, this, because I'm sending 2 bits, more or less double. So you can see now it's 16 bits per second. Of course, if I could send 4 bits in one signal, it makes it even faster. Does that make sense? So encoding depends on how many levels. And again, there is a pattern. Now we can see it. So if I want to encode 2 bits, I want to encode 2 bits, how many levels do I need? 2 bits, I need 4. I want to encode 1 bit, I need 2 levels. You see the pattern? I need to encode 3 bits. How many levels do you think I need? 8. So what is it? 2 to the power 3. 3. So basically, number of levels needed is 2 to the power. How many bits you want to encode? If you don't believe me, to do it. So this was 1 0, 1 1, 0 1, 0 0. All the combinations 0 0, 0 1. You know that's why I need 4 levels. Think about it: 0 0, 0 1, 1 0, 1 1. Hence 4 levels I need. Does that make sense? So suppose now I told you I have 3 bits. So it's going to be 0 0 0, 1 1 1, and all the other combinations: 0 1 1, 0 1 0, 1 0 0, 1 1. You know, I keep on doing it. How many will it be to be 8? If you don't believe me, you can do it yourself. Okay? It'll be total of 4, so not 6. Are we good? So if I want to go backwards, if I want to know how many, again, typical question, how many levels do you need given the bits? That's easy. Now, what if I told you I have a number of levels? How many bits can I encode? See if you're smart.
It's just with the log.
Yes, who's talking? Yes, Joseph's on fire. Yes, Joseph, very smart. Yes, of course. This is exponential function, my friend. So if it's 2 to the power on one side, the inverse of power is not square root. The inverse of power is logarithm. So it's an exponential. So I take log base 2 of the levels. I know, for example, log base 2 of 4. What's log base 2 of 4? I have a marker here. I have a marker. Yes, I do have a marker. So, of course, log base 2 of 4, which is basically 2 square, right? So log base 2 of 2 square, 2 is 2. Log base anything of the same base to the power of anything is the power. I mean, that's basically the issue in basic algebra. So yes, of course, if I told you I have 4 levels, how many bits can I encode? That's what we care about. I can encode. If I have 4 levels, how many bits can I encode? 2. If I have 8 levels, how many bits can I encode? 3. So 8 is 2 cubed. So it's 3. And so on. So this is the backwards. Now, if I told you how many levels do I need, I square it. So if I have 2 bits, how many levels do you need? Level. Does that make sense? So this is kind of the inverse, opposite. And we usually care about this. Okay? Of course, if it's not the whole number, suppose the number of levels is I don't know, 17. 17. Okay? 17. What do you think? How many bits can I encode? So log base 2 of 17.
Log
So
17.
17 is 16, very close to 16. 16 is 2 to the power 4. So it's gonna be basically 4 point batata, right? Because it's gonna be a little bit higher than 4, because 16 is 4. You know what I mean? So 4 point something. So how many levels do I need? How many bits can I encode? Right, round up or round down?
Down.
Down, of course. So how many can I encode? 4. It's not 5. Of course, 5 is way more than 17. Be 2 to the power 5 is 32. Does that make sense? So be comfortable with this. I mean, there's like 4 or 5 of you talking to me. I know you know what you're talking about. The others, I'm worried about you guys. So good luck. Okay. So as we said, yes, log base 2. Suppose I have 8 levels. I could encode 3 bits. Suppose I have what is this? 9 levels. Again, of course, in this case, I can also encode 9 is still 3. So I cannot encode 3.17 bits. I could encode a maximum of 3. Okay, so we round down. So what is the bit rate of HDTV? A simple question. We have the number of pixels. It's renewed 30 times, 24 bits represent one color. So we can get the actual bit rate. Let's multiply everything. You can get that the bit rate of high definition TV is 1.5 gigabit per second. So if you're looking at HD TV, not 4K HD, it's basically 1.5 gigabit per second. Again, based on the information we have. It's again very simple question. So the time and frequency domain of periodic, just to summarize, and non-periodic, 4 times. You can see, like we had there analog signals. Now we have digital. So I'm just showing you it's the same thing. Digital signal, we get spikes. You can see again, if it's periodic and non-periodic, you get a continuous signal when it comes to frequency. So time domain, frequency domain, very similar to what we do with analog signal. Nothing changes. The logic is the same. Okay. So usually, guys, we have a digital signal and a channel, and we send it from one computer to another. Again, fiber optics, baseband, coaxial cable, USB, HDMI cable. All these are digital mediums. So therefore, I'm sending digital signals. Okay, so that's the typical scenario. Of course, My data here originally is digital data, it's a computer. So I have to convert from digital data to, here, digital data to analog. No, not analog, not analog. Digital data to digital signal. Thank you. Digital data on my computer to a digital signal that could be transferred on the media. Okay, so that's what we usually do in this kind of scenario. So yes, digital signal is a composite analog signal with an infinite bandwidth. So let me just show you here. So typically we have something called low pass and high pass filters. Again, the idea of these is very simple, is to allow specific signals to pass through. Think about them as a filter. So we usually have them in a medium, say, oh, this is a low pass filter, high pass. What does that mean? So you can see this is an example of a low pass channel and wide bandwidth. So you can low pass meaning it has a wide bandwidth. High pass usually, again, in this case, one is both of them are low, but you also have high pass filter. What does that mean? It allows specific bandwidth to pass through. In this case, it's wide, it's allowing a lot. In this case, it's narrow, allows a specific signals to pass through from here, 0 to F1. Okay? So if you look at baseband transmission, remember I talked about baseband, coaxial cable, meaning it's digital. So if you look at the baseband transmission, the input signal, this is my bandwidth. When we send it over a medium, what we get, the output signal, you can see, is not the same, right? Of course, it's affected by noise, one, and it's affected by the bandwidth supported by the medium. So in this case, that's what I want, that's what I have. You can see some of it is cut, and that's what my output signal was looking. Okay? So what am I trying to tell you here? So it's not always what I send is what is received. Because one is noise, two, because of the low pass or high pass filters that we have in between. So what we need to do at the other end, we need to transform it back to the original. And there are techniques to do this, okay? So we need to preserve the shape of the digital signal if possible, using a low pass channel with a very high bandwidth. So of course, if I have a very wide bandwidth, I will typically preserve the signal itself. Okay, so an example is a local area network has a dedicated channel for each station, and that's considered as a very wide bandwidth. What does that mean? Meaning we usually preserve the signal quality and conditions. So baseband, the bandwidth is proportional to the bit rate, as we know. Of course, if you want to send more bits, you need more bandwidth. That's kind of intuitive. If the channel is a band pass channel, we cannot send the digital signal to the channel, we need to convert it. So what does band pass mean? Band pass meaning analog. So if I'm sending digital data over an analog signal, I need to convert it. I need to do some conversions, and this is some techniques that we have. So give you an example, using a modem, that's what happens. I have a digital signal coming in. I need to convert it into an analog. So one more time, it looks like this. Now it looks like this, using the technique either amplitude, shift keying, or frequency, or phase. Anyways, we convert this to this. We send it over the medium. And fast meaning analog. So I'm sending an analog signal. Then when it comes here, it comes as an analog signal, and I convert it again into a digital data. Does that make sense? So this is a typical scenario of what we do every day. You know, if you're talking over a microphone, over the internet, voice over IP, typically that's what's happening. Of course, the converter usually is the modem, the modulator, and demodulator. Okay? Are we good? Just to see how I'm doing with time. We still have time. Very good. So let me just finish this, and I'll allow you questions. Let me just finish, please. So let's move on. So again, broadband transmission example. I'm just going to move fast forward with these to talk about. I just skipped a couple of slides just as examples. You can read them. So what could happen to the signal on the way? We already talked about this a little bit in one of the tutorials before. I want to talk about them more. Typically, when I send a signal, there are three kinds of impairments. Impairment meaning something could happen to. To be specific, it's attenuation, distortion, and noise. Okay? So my signal could be affected by three things, most likely. So what are these three things one more time? Attenuation. We talked about attenuation before. What does attenuation mean? What happens to the signal? Yeah? It's not, don't lose it, but it attenuates. What does it mean? Not distortion. That's smaller. Typically, the amplitude goes down. Now we know. Now we know what amplitude means. So attenuation means the signal is kind of dying slowly. Amplitude is going down. What do? We amplify it using amplifier. Using an amplifier. You know, if it's analog or a repeater. So we amped it up, right? That's what an amp is for. So because the signal is attenuating, because over a TV, especially if you're using a specific cable, it doesn't handle long distances, so my signal will attenuate. Okay? The other one is distortion. You get distorted. Again, typically by external signals, by other signals. Very similar to noise, you know. And the last one is the noise itself that we are worried about. Again, any kind of noise. It could be electrical noise, it could be lighting, it could be anything happening around it. We refer to as noise. Okay, hence we have signal to noise ratio that we'll be talking about. So typically, this is attenuation. As you see, at one point I had the original signal, it attenuated, so the amplitude went down, and then I amped it up, I got back the original signal. Okay, the problem with amplifiers is yes, I amp it up, but what do I amp with it? Noise. That's the problem. That's why I need to do filtration before I need to filter. So imagine if I have noise and I'm increasing everything. You know, suppose I'm listening to a bad quality music. Yeah, I amp it up, put the volume higher. What will happen? Everything will come up. You know, not only the voice of the music, every jump with it will be amped. Okay, so that's why usually we need to be careful with this. So distortion. This is an example of distortion. So the sender. These are my components. You can see the constant signal. It got distorted. You see, compared to what I said, it's distorted. You know, it's like again, typically because the components kind of differed a little bit, which led to a distorted signal. And the last one is noise. At one point, I have my signal and I have another signal, which will kind of be superimposed over it, which will give you something like this. Especially if this noise is big, it's going to affect it big. So talking about this, we have something called signal to noise ratio. That's what we care about. We already talked about it in one of the tutorials. The signal to noise ratio is basically the power of the signal divided signal to noise ratio. The power of the signal divided by the power of, that's what's called signal to noise ratio, SNR. Power of signal divided by power of noise. So if I have both of them, I could know SNR. Is it good to have a big SNR or a small SNR? Of course, big is better always, right? So big is better, of course, because signal over noise. If I increase signal, then signal to noise ratio would be bigger. If I increase the noise, you know, then if I'm dividing signal to noise, I want my signal over noise, because if noise was big, this number will go smaller because it's my denominator. I'm dividing by it. That's the idea. Okay? Very good. Anyway, so you have to make sure, if I want to convert this to decibels, remember, signal to noise ratio, what's the unit of it? What's the unit of signal to noise ratio? No unit, it's a ratio. Of course, there's no unit. But if I want it in decibels, because it's easier to play with, we do 10 log base 10 of this. Okay? Some people call it 20 log. We usually go with 10, depending. Either way is fine with me in the exam. But 10 log base signal to noise ratio, if I want to convert this to decibels. So again, make your life easy as quickly as possible. If I have 4 zeros, then in decibel to be, basically in decibel is how many zeros you have in decimals. So 4 zeros, what would it be there? 40. Just because of multiplying by 4. Yes, 40. So if it was a million, it would be 60. You know? Very easy. You don't have to even do calculation. At 1 point in time, it's so easy to do. Okay? Because it's log base 10, no? Log base 10 here. In case you're wondering. So this is log base 10. Okay, for example, this case, this is how many decibels? How many decibels? How many decibels? 40. Thank you. Okay. Yeah? We good? We good today? Yes, tell me. It's your problem, not mine. I have my own lecture as well. I don't care. This is a lecture you're enrolled in, so you have a conflict. You decided to take 2 courses at the same time. So what can I do? There's 120 students here. So please, anybody who comes and says, I have another course, I have another thing. Sorry, no offense. You decided to take this, not me. My course is still running till 2:30, right? Yeah, till 2:30. What time is it? Yeah, we have time. What time? Okay. So let's move on. Okay, so these are an example of high signal to noise ratio and low signal to noise ratio. Okay, so officially, let me stop recording. Officially,